A register is a digital circuit which can store a few bits of data. It's an essential component of a CPU since the CPU registers hold the temporary data during any computation. The register which we'll design today should have these basic features. It should have bidirectional data input lines. The same data bus should be used to both read and write data. It should have a chip select signal. All operations can be done only when chip select is 1. Otherwise, the data bus should be tri-stated. It should have a write enable signal. If write enable is 1, data should be loaded into the register at the next passage of clock. An output enable signal. If output enable is 1, the data bus should reflect the register contents.
All these points are encapsulated in this truth table.
It might be more precise with this timing diagram. When chip select goes high and write enable is also high, the data at data bus will be latched on to the internal data at the passage of clock. Similarly, whenever output enable goes high, the data bus will be loaded from the internal data. And when chip select is low, the data bus will be tri-stated.
Let's code this in Verilog now. I'll declare the inputs here. Data should of course be an in-out port. Here's the data int signal. It should be of type reg since we expect it to hold its value. Here's the reset condition. In-out ports should be treated like wires and should therefore be continuously assigned. I'll use the ternary operator to assign data. If chip select is 0, output should be tri-stated. If chip select is 1, then output enable should decide. Now in the clocking block, I should have the write logic. I'll be coding in the truth table here. This is the write condition. As I said earlier, WE and OE cannot both be 1 together, so I'll display an error here. We won't be able to do this in structural modeling, however. Now it's time to code the TB. From now on, I'll use this basic TB template to code all test benches. This is the includes header file which has all the DUT code. I'll replace the basic TB module name with the register TB. Here I'll finally define my data width variable and set it as 8. But we can set it to anything we want, 4, 32. Timescale specifies the time unit, which is the measurement of delays in the simulation. The wire array data bus will be the system data bus. We can pass this to the register. Initializing all the input variables. a monitor statement to display everything. Here I'll instantiate the duty. Now here I'll define two tasks, do write and do read. Their purpose is to write and read data to the register. I'll follow the timing diagram to assign these signals in order to read and write to the register. I'm using non-blocking assignment here since I want these signals to change their value together, but it really shouldn't matter as long as we follow the timing diagram. Now for the stimulus, I'll write and read a bunch of random data and see if it matches. Finally, I'll intentionally cause an error at the end by setting OE and WE high at the same time to see how the DUT behaves. Now let's look at the waveforms. You can see all these prints, even the error prints from the end. Now let's look at the waveforms. Clock, chip select, OE, WE data and data end. BF is written at the pause edge, then AD is written, and after that AD is read, and so on. It looks like it's behaving as expected. Let me remove the delays and see how fast we can write and read. Let me save the signals first so that we can reuse it.
I know that you're the one for me, but we have some differences and they're so obvious. Oh.
It's the same as before. BF is written, then AD is written. We're able to write and read at every clock cycle. Now let's look at the circuit diagram.
this is the internal structure of the register for each bit. This structure should be replicated for all n bits of the register. Here we have a D flip-flop, a tri-state gate, and a latch. To read the input, we must enable the tri-state gate by ANDing chip select and O output enable signal. To write the data bus content to the register, we must enable the latch by ANDing chip select and write enable signal.
Now let's code this in Verilog. I'm copying it from the behavioral model and I'll remove all the statements. Once we have figured out the circuit for one bit, we can replicate it for all n bits using the very useful Verilog generate construct. I'll be using it all over this project. Whatever is inside this for loop will be replicated n times. I'm setting n as data width. Just 3 components are necessary as shown in the figure: a flip-flop, a latch, and a tri-state gate. I haven't created the latch yet, but if you remember the D flip-flop video, I had created a level triggered flip-flop and then discarded it, but that's exactly what a latch is. So let me code it quickly before using it here. Here's the D flip-flop circuit from earlier. I'll create another module called latch. I'll just copy the level triggered code here and hopefully it should work. Replacing clock signal with N. And now we are ready to use it at the register module. Wiring everything up according to the circuit diagram. Chip select and write enable. And finally, we have the tri-state gate. Chip select and output enable. And there we go. Let's simulate it and see if it works. I'll comment out the switch to structural modeling. There are no simulation errors and there are no error prints either, which is not surprising. Now let's look at the waveform. I'll load the saved file we saved earlier. We know it's a structural model because all the hierarchies are present inside Reg 1. This dump is pretty similar to the last one. All the data is being read and written as expected. Now I'll add the delays again and give it another go. This is a very crude way to verify the register, but it should be fine for my purpose. BF is being written here, AD is being written here, AD is being read there. So yeah, it's behaving as expected. So today we saw how to design a register with bidirectional data lines. Later we can use this design to create CPU registers and counters. Thanks for watching.